Hello, my name is Lily Alterman, and today I'll be presenting to you Lab 4 bar magnet. So now the purpose of this lab was to measure the distance-dependent magnetic field of a relatively small bar magnet, and then, using web, Python, and experimental data, compare the observed versus predicted distances of the on and off-axis magnetic field. Now, some of the results of this lab, the n factor ended up being negative 2.7624, k ended up being 1.0227 times 10 to the negative 6, the magnetic dipole moment ended up being 5.1135, and the computed and experimental magnetic fields at the 45 degrees varied vastly. Now, as a little introduction, Savant law describes the magnetic field generated by a constant electric current, and for point charges it is depicted as this equation right here, with this little mu naught over 4 pi being the magnetic constant, and the rest, q being charge, v being the velocity, r being the just r vector, and then this will be the magnitude of r squared. And then the magnetic field of a dipole. The magnetic dipole is a model of an object that generates a magnetic field distinguished by two opposing poles, north and south, and this equation right below here is just the general form for finding the magnetic field of a dipole. And the most important part is this mu right here is the magnetic dipole moment. And then the magnetic field due to a bar magnet is distance dependent, as the magnitude of the magnetic field decreases as the observation point is moved further away from the bar magnet. And these two equations right here we're going to be using later in the lab to help us calculate that. So now as a little introduction, the programs I used for this experiment were WebPython and PHYS, which is a mobile app. Also, as a little note, I used this app on iPhone 13 iOS mobile operating system, and here's just a little picture on the right of the app in use. Now for the experimental procedure. To set up, I downloaded and installed the app. I aligned my phone with the Earth's magnetic north to compensate for external fields and make that not interfere with my data. And I also identified the locations and the location of the phone's magnetometer sensor. And then for the on-axis magnetic field part of our experiment, I placed the bar magnet at one end of the meter stick, and I used the magnetometer app to measure the x component of the magnetic field at various distances and recorded the data. And for the off-axis magnetic fields, I adjusted the setup to measure the field at a 45-degree angle from the original axis, and I recorded the measurements and corrected the data to account for Earth's field. Now the initial conditions, I assumed that the Earth's magnetic field is the only other magnetic field I needed to account for, which I did. I also assumed that the phone is able to read and measure the magnetic fields properly. I assumed that bar magnets act as a magnetic dipole, and I also assumed that the magnetic field caused by the bar magnets fall off as distance increases. For the system, it was the bar magnet, the phone, and the meter sticks, one or two, depending on what point in the lab I was in, and the surroundings were just everything else around the lab, including the table, my computer, myself, and my lab mate, all of that. And then up above, right on the top right here, this is the on-axis experiment setup, and the off-axis experiment setup is right below it. Now for the experimental data, right here is just all the data we got from our different distances and our different magnetic field data. The most important part will be this linear equation right here, and we're going to come back to it in a few slides, but it's going to help us calculate our magnetic dipole moment. Now, and then for our off-axis data, here was a little setup right here. Basically, we got our distance perp to be able to calculate our distance d right here for the 45-degree angle, and then we use this to correct it and account for the magnetic field from gravity, and then we were able to get this v-net right here, and we'll come back to this data point 2 later in the lab. Now for the magnetic dipole moment calculations, we took this linear equation, the slope of it did equal n directly, and the y-intercept ended up being the natural log of k, which we then used converting formulas to get our k value as 0.100227 times 10 to the negative 6. Then I was able to set the b-bar equation up to the b equation of the general form, and then by setting those equal to each other, I was able to get the magnetic dipole moment to be 5.1135. Then I used that, I plugged those data points right into my WebPython simulation. This is just the constant up here, the magnetic constant. Down here, I just plugged in the magnetic dipole moment I previously calculated. And this formula right here is just put in the code for the magnetic field of a dipole. Then right here, this part of the section of the code made our orange arrows. This section of the code created the observation locations. This section of the code created the purple arrows. And these were all used, including the scaling at the bottom, to print to the shell. And then also, I used this formula right here to find the pink arrow, which was the 45-degree off axis. And all of these ended up printing to the shell while also calculating the values for me, which were the following. All of these were the b axis, 1, 2, and the perpendicular axis is 1, 2, 3, and 4. Here was my distance and my b vector at 45 degrees at distance d. And then here was a little alternative view, obviously pink, 45 degrees, the on axis were orange, and the off axis were purple. Now some of the results. The computed off-axis field by the WebPython simulation was 6.917 times 10 to the negative 2 power, while the experimental off-axis field was 5.681 times 10 to the negative 5th power, and these differed vastly. Some of these errors could have came from the fact that there was an not exact location for the magnetometer. I kind of had to estimate that, and I could have been wrong. There was also other objects in magnetic fields possibly skewing the data. I did have my computer out to transcribe and write down the data, And also my phone could have just been inaccurate in reading that magnetic fields. During this lab, we were getting very differing values, and our magnetometer was varying vastly while we were trying to take the measurements, so that could definitely be an issue. And then my observations were when the magnetometer was very far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, it measures the x component of the magnetic field increasing. Now the what if? Basically, the data would have been further skewed as the Earth's magnetic field would have interfered with the bar magnet's magnetic field, and the other what if basically meant that if the magnetic field would have been doubled, but it would stay in the same direction as only the magnitude was changed, not the direction, as the two identical magnets would almost be like batteries in series and just combine together. Now, thank you so much. Have a lovely day. Thanks for watching.